Concrete is the most commonly used material on Earth, but its prime ingredient, cement, is not kind to the planet, at least in how it's traditionally made. But new technologies are quickly transforming the industry.
Every year, China produces more than 2.1 billion tons of cement, the largest output the industrial world has ever recorded. That ordinary-looking gray powder is the hidden backbone of the country's massive bridges, cross-country highways, underground metro systems, and rapidly growing cities, all rising at a pace unmatched in modern history. But before it becomes the foundation of trillion-dollar megaprojects, cement begins as raw rock buried deep within mountains. These rocks are blasted apart, crushed by machines weighing hundreds of tons, heated to more than 1,400 degrees Celsius, and then shot-cooled to create clinker, the essential ingredient behind every concrete structure. Powering this transformation is a non-stop, 24/7 operation where every ton of rock is turned into one of the most crucial building materials of the 21st century. And how China manages to achieve this scale, that's what you're about to discover. The massive flow of cement China produces each year generates more than $200 billion, making it one of the country's core economic engines. Its scale surpasses every major economy on the planet. In just 3 years, China used more cement than the United States did throughout the entire 20th century, a clear sign of an infrastructure boom few nations can match. Provincial expressways, a high-speed rail network stretching over 40,000 kilometers, and megacities like Shenzhen, Pudong, and Tianjin were all built within a single generation, powered by this enormous cement industry. But such speed comes with significant costs. Cement plants consume nearly 8% of China's total electricity, emit more than 820 million tons of CO2 each year, and produce vast amounts of fine dust that place heavy strain on the environment. Even so, to maintain its position as an infrastructure superpower, China accepts these trade-offs, viewing cement as the raw fuel behind its rapid national ascent. The raw materials powering China's massive cement industry begin in the limestone mountains that surround its major industrial zones. Limestone makes up 75 to 80% of the raw mix and provides nearly all of the calcium oxide, the key ingredient that drives clinker formation. To minimize transportation costs, most cement plants are built directly beside these quarries, making extraction the first link in a production chain that runs non-stop, day and night. Across the quarry surface, geological engineers map out a grid of drill holes, each 8 to 12 meters deep, positioned in precise directions to create a controlled break. These holes are packed with emulsion explosives or ANFO, along with electric detonators and stemming materials, all designed to maximize blasting efficiency. When warning sirens echo through the site, the blast sequence begins, tearing apart an entire bench and producing thousands of tons of fragmented rock exactly along the plan line. As the dust settles, large crawler excavators move in to load the rock onto 40 to 60-ton haul trucks or directly onto primary conveyor belts leading toward the plant. Oversized boulders are broken down on the spot using hydraulic breakers to prevent jams at the crusher. At the primary crushing station, jaw or hammer crushers reduce everything to under 100 millimeters, the ideal size for blending and fine grinding later on. Along with limestone, clay is also extracted from nearby open pit deposits using large bucket excavators. This area doesn't require blasting, but it does demand strict control of moisture levels, chemistry, and consistency. Even small variations in the feed can throw the entire clinker production line out of balance. Once extracted, the raw materials enter a fully mechanized transportation system. At many modern plants, limestone and clay are moved continuously through closed-loop conveyor routes. Kilometer-long belts link the quarry directly to the industrial complex, crossing hillsides, valleys, and technical zones without a single stop. This steady, uninterrupted flow keeps costs low and prevents bottlenecks at the primary crusher. In more challenging terrain, heavy-duty dump trucks still support the main transport line, delivering additional material to ensure a consistent supply for production. Upon reaching the processing area, the materials enter the homogenization system, a critical step to stabilize chemical composition before fine grinding. From the main conveyor, limestone and clay are fed into the dome storage facility at a controlled, even rate. Inside the storage dome, a stacker distributes the material in thin, arched layers, creating a perfectly structured pile that spans the entire floor. On the opposite side, a reclaimer glides along the pile, recovering the material in the exact order it was laid down. This layer-by-layer stacking and reclaiming system evens out variations between quarry batches and guarantees a steady, uniform feed for the production line. The blending stage begins as the homogenized materials move into the automated dosing system, where belt scales constantly measure and adjust proportions according to the plant's design formula. Once the mix reaches the required ratios, it's sent to the grinding unit. The most energy-intensive step in the entire process, and the one that ultimately determines the quality of the raw meal before it enters the preheater tower. Depending on the plant's technology, the mixture is fed into either a vertical roller mill or a multi-compartment ball mill, massive machines capable of running continuously and processing anywhere from 100 to 500 tons per hour. Inside the grinding chamber, intense compressive forces and friction from rollers or steel balls reduce the material to particles smaller than 90 microns, producing a highly uniform raw meal. Some older production lines still rely on wet grinding, where water is added to form a slurry. While this method simplifies chemical control, it consumes far more energy and is gradually being replaced by modern, efficient dry grinding systems across the industry. All operating parameters, including feed ratios, grinding speed, fineness, and gas temperature, are monitored in real time by the SCADA system to ensure the raw meal stays stable and consistent before moving to the next stage. Inside the preheater tower, heat from the rising hot gases spreads upward, but the raw material follows its own controlled path before reaching the harshest environment, the rotary kiln. From the top of the tower, the limestone and clay mix drops into tall cyclone chambers, spiraling downward as it meets the upward flow of hot air. Each cyclone works like a natural preheater, quickly raising the temperature of every particle to around 850 degrees C. In the calciner, the core of the tower, carbonates break down almost completely, transforming the raw meal into minerals ready for high-temperature reactions. This multi-stage structure functions like a vertical river of material, weaving through steel chambers and absorbing energy from the burners below. Coal was once the primary fuel source, but to reduce costs and emissions, many modern plants now supplement it with alternative fuels. Shredded rubber from old tires, cleaned of metal and processed into chips, is injected directly into the burner, burning intensely at nearly 1000 degrees Fahrenheit. The alternative fuel delivers energy comparable to coal while producing far less CO2. The entire process is tightly regulated through automation, controlling material drop rate, airflow pressure, and cyclone temperatures to prevent both over- and underheating. Even as the material moves rapidly, every step targets two core objectives: maintaining a consistent feed to the kiln and reducing environmental impact. It's how China's cement plants balance enormous production levels with increasing pressure to make the industry greener, a clear reflection of the country's infrastructure ambitions. The deep rumble of the rotary kiln blends with the glow of its red-hot flame, creating a steady industrial rhythm. Inside the long steel tube, raw meal from the preheater enters and slowly travels along the refractory lining, turning with the kiln's slight incline. As it approaches the hottest zone, each grain of limestone and clay is subjected to more than 1180 degrees Celsius, where its original structure begins to break apart and reorganize into new minerals. At these temperatures, CO3 rapidly decomposes, releasing CO2 and forming highly reactive chow. The chow then combines with silicates and illuminates in the mix, producing the essential clinker phases: alight for early strength, belight for long-term strength, and illuminate for setting behavior. This is the most critical stage of the entire process, where even minor fluctuations in temperature or retention time can lead to underburned or overburned clinker. To keep conditions stable, the control system continuously tracks kiln speed, fuel flow, and gas pressure using heat sensors and infrared cameras. Burners inject fuel in a swirling pattern, creating a long, penetrating flame that drives the reactions to completion. The swirling flame transfers heat deep into the material bed, while hot gases from the decomposition reaction are drawn out through the kiln inlet, carrying most of the released CO2. Excess heat is recovered and redirected back into the preheater system. As the material moves along the kiln, it gradually fuses into glowing red clinker nodules, rolling steadily along the kiln's axis in the constant roar of fire and steel. Still radiating heat, the red-hot clinkers slide out of the rotary kiln and flow directly into the cooling system. On the moving grate, powerful blasts of cold air rise from below, taming temperatures that still exceed 1000 degrees Celsius. Each clinker slowly shifts in color as it cools, sending waves of heat upward in steady pulses. The haze of warm air blends with the fading red glow, creating a vivid scene where heat, motion, and machinery merge to stabilize the clinker's mineral structure. Even after cooling, residual heat clings to the clinkers as they enter the high-capacity grinding mill, which processes several hundred tons per day. Here, the clinker is combined with 3 to 5% gypsum and mineral additives such as fly ash or ground granulated blast furnace slag. Under the continuous pressure and friction of steel balls or rotating rollers, the mixture is ground into fine cement powder with a fineness of around 4,500 micrometers per gram. Fine dust drifts into the air, and the reflected light on the machinery gives the entire scene a mechanical yet almost living quality. Automated dosing systems and sensors monitor each batch, ensuring consistent mineral composition, fineness, and strength, transforming solid clinker into the refined foundation of high-quality cement. The finished cement powder falls into the intermediate silo, moving with a steady, river-like flow. Inside the plant, an automatic sampling system extracts a portion of the powder and delivers it to the laboratory, where advanced sensors and analyzers measure key parameters: fineness, moisture, mineral balance, and strength development. Each test result is continuously compared against internal standards and national specifications, ensuring every batch leaving the plant remains uniform and stable, a place where mechanics and precision flow together in an almost living rhythm. From the silo, the perfectly blended cement powder moves into the packing area, where the plant's rhythm becomes a steady stream of material. Each empty bag is positioned beneath the filling nozzle, and exactly 50 kilograms of cement drop in, controlled by a modern dosing and weighing system. The automated packing line runs seamlessly, producing 500 to 600 bags per hour, creating a scene that feels both mechanical and alive, the soft sound of falling powder blending with light reflecting off metal surfaces. In advanced facilities, robots have fully replaced manual handling. They position the bags, fill them, seal them with heat or tight stitching, and verify the accuracy of each closure. As the filled bags travel along the conveyor, sensors scan them one by one, automatically removing any that fall outside the required specifications. Further down the line, robotic arms stack the bags onto pallets with brick-like precision, 40 bags per pallet, before the entire load is shrink-wrapped. Under the warehouse lights, the smooth plastic glints off each tightly packed bag, forming a refined industrial scene where machinery, automation, and precision move in perfect harmony, completing the final step before the product leaves the factory. As it leaves the automated warehouse, the cement is transported to concrete batching plants, where it meets its familiar companions: fine sand, crushed stone, and clean water. Automated dosing and mixing systems adjust every proportion with precision, ensuring each batch of concrete achieves perfect uniformity. Within minutes, this seemingly simple gray mixture transforms into a foundational material, ready to support massive structures, from river-spanning bridges stretching thousands of meters to skyscrapers and expressways worth billions of yuan. Every concrete element carries the mark of advanced engineering, automation, and strict quality control. The sounds of mixers, conveyors, and concrete trucks blend with the rotation of tower cranes, creating a rhythmic industrial symphony. Every grain of sand and piece of aggregate is carefully monitored for weight and size, while roller vibrations and slight temperature changes are tracked to guarantee structural stability for centuries. In this vast landscape, concrete is more than just a building material, it is a symbol of technical strength and modern infrastructure. Across China's trillion-yuan megaprojects, technology and labor converge to shape enduring greatness. From these refined materials, cement becomes the solid foundation behind China's modern, massive structures. Every bag of cement and every batch of concrete embodies precision, technology, and mechanical rhythm, contributing to the construction of bridges, highways, skyscrapers, and trillion-yuan projects across the country. This story is more than just about materials, it is a testament to the seamless blend of labor, engineering, and automation, where quality and performance are carefully managed at every step. If you found this journey fascinating, be sure to like and follow Manatech Explorers too. Explore more engineering marvels and infrastructure wonders from around the world.